Welcome. This question says a 4-kilogram car moves on a banked circular track that has a radius of 5 meters. The banking is designed so that the car does not rely upon static friction when traveling at optimum speed. If the track banking makes an angle of 20 degrees to the horizontal, what is the optimum speed for the track? So let's visualize. We'll have banking is the car, is its normal force, no frictional force of course. We know that the radius is 5 meters. We know there's going to be a weight of course, and the weight is going to be 40 newtons. And there's a couple of more things we know. We know that there is a centripetal acceleration because that's what enables the circular motion. And so we say, well, okay, let's try and find. The other thing we know, the other thing we know is that this thing is moving. I draw it like that. This thing is moving with a certain velocity, tangential velocity. So what we say is that, and I'm drawing this like as if it's in a circle. It's really coming out the page towards us. Okay, so let's begin. I say, well, the sum of my forces horizontally is equal to ma, because there's this centripetal force horizontally, which equals mac, which equals mv squared over r. And typically what we do is we always look for where there's an acceleration and resolve our forces in that direction as our first step. And here we see that, well, we have Fn. Now let's be clear here. If that is theta, that's the angle to the horizontal. If that is theta, then this is 90 minus theta. And if that's 90 minus theta, that is theta. And this is 90 minus theta. Let's put numbers in. It would be a lot easier with numbers. Because I actually know the numbers. So if this is 20, then that's 70. If this is 70, that's 20. And if that is 20, that's 70. Okay. So we can say, oh, Fn cosine 70 is equal to m, which is 4 v squared over 5. So we can say, oh, well, v squared is equal to Fn cosine 70 times 5 over 4. And if we knew what Fn was, we'd be done. But we don't know what Fn is. So let's have another go at this, and we're going to say, okay, the sum of the forces vertically equals 0. If the acceleration is horizontal, then there's no component of it vertically. And so we can say the sum of the forces vertically equals 0. If we look at this, we're going to say Fn sine 70 added to minus 40, because that's going to be the downwards force of the weight, is equal to 0. If I were to draw that in, this is the Fn sine, and that would be the Fn cosine. So I've broken that up into the two components. What this means is that Fn is equal to 40 divided by sine 70. So v squared is equal to 40 over sine 70 times cosine 70 times 5 over 4. All my numbers can be worked out now. So we have 40 divided by sine 70 equals, multiplied by cosine 70 equals, multiplied by 5 equals, divided by 4 equals. I try not to use a whole bunch of parentheses because that's when people tend to make mistakes. I try to break the calculation up into a lot of little steps. And that's 18.20. So v is equal to the square root of 18.20, which equals, so I go second square root, second answer, and I'm getting 4.27, I think that is, 4.27 meters per second. And I look on here, and there it is, 4.27 meters per second. So, as usual, we have a decent diagram to begin with, and we look for the acceleration, and we resolve our forces in the direction of that acceleration. In this case, we know that the acceleration is a centripetal acceleration, so we know it equals v squared over r, and we try to solve. And if we don't have all the information, so we cannot solve it in one step, then we go at 90 degrees to our original direction, so now we're going vertically. And this is the only direction in which we know that the sum of the forces equals 0. And we get a second equation. We can use the second equation to isolate Fn, the normal force, which we substitute into the first equation, and we work out and get our number. Looks complicated, but there it is. It's a relatively simple and straightforward problem. Incidentally, a lot of roads are designed this way. A lot of interstates have just the right angle so that if you're driving at about the speed limit, then you don't even have to turn the wheel. You will just go around a bend just by making normal progress. And one time I had to actually stop on a curve like this. It was an emergency stop. And I was stunned once my car was stationary at the angle I was at. I was at quite a steep angle. And suddenly everything in the car is leaning over to one side and getting back into traffic when you're starting off and you're at such an angle doesn't feel like a natural thing to do. So this is good engineering. It's a part of everyday life. We just don't necessarily notice it. So there we have it.